3.1, we're going to talk about the extrema of functions. So here I have listed 4 items. These are the objectives of actually chapter 3, not this section, but in chapter 3. Part of this would be the objective of this section. But all in all, in chapter 3, we are interested in trying to obtain information about a function through an interval. Okay, so I have listed some of the things that we may be interested in. For example, the high points, the low points, places where the function may rise or fall, the extreme values, if they exist, of the function. And again, by extreme values, we're talking about the maximum or the minimum values of the function. And we're going to also look at some of the theory that actually connects derivatives to extreme values. And by that, more specifically, I have the mean value theorem in mind. Okay, and near the end of chapter 3, we're going to take a look at these other 2 items. One is called Newton-Raphson method for approximating zeros of a function that are solutions to equations. And near the end again, we're going to take on the topic of optimization. And by that, again, we mean the maximum or the minimum value of a function in an applied problem. So that's going to be the agenda for the entire chapter. So in section 3.1, let's talk about what we mean by extrema of functions and how to actually obtain them. So here I have the definition of the extrema of a function. So our first definition reads, let's say we have a function that's defined on a set of real numbers, and then C is a number. It's a real number inside of that set. Okay, C is a value of X. So 2 parts to this definition. Part 1 is definition of a maximum of a function on that set S, and it's defined as f at C is a maximum of f if f of x is less than or equal to f at C for all x in S. Again, the symbol that I have here, this is the universal modifier. That means for all or for every value of x inside of that set. So in other words, if you look at the graph, which I have just below that, there is no point on the graph higher than f at C, at that point. And this would be the point on my chart right now, on my graph. Okay. Now there could be other points equal to that, but they cannot exceed it. Okay, that's why we have less than or equal to it. And that's the definition of a maximum. So remember, maximum, there's no point higher than that at C. And minimum kind of defined in a similar fashion. In the case of a minimum, we're looking at the value function that's minimum on a set if there is this time no point lower than the one at C. Okay, so f at C is going to be again the low point of the function. Now these extrema together, minimum and the maximum, are called extrema, which is the plural world. And the singular version of that word is going to be extremum of f. So if I have a single max, that would be the extremum of f. But if I'm looking at both max and minimum, let's say, for 2 different purposes, then I'm interested in the extrema of the function. Okay. Now if we have a constant function, because the constant function, remember, it flat lines. So for constant functions, any point on the graph of a function is going to be a maximum or a minimum, because it flat lines and it satisfies the equal portion of the inequalities above. Okay, so for that reason, a constant function is both max and minimum at any point. Now, as far as taking on a maximum or a minimum, it is possible for a function to attain the maximum or the minimum at more than 1 point. So the what you see here is kind of like a sine wave for this one. And here we have the case where the function takes on more than one maximum and more than one minimum. Notice it can have both of those and multiple values of x at which the max or the min occur. Okay. Now, and then we have what we call a global or absolute extrema. If we look at the maximum or the minimum of a function over the entire domain of the function, like in the case of maximum, there is no point higher than that over the entire domain, then we're looking at global extrema. Okay, so for example, let's say I have a function that behaves this way, like that. So in this case, this point here, and let me make it go the other way like that. So at this point, this would be a global max, because over the entire domain, there is no point higher than that. Okay. Now in the case of what I have here, looks like the global min may be 0 eventually, depending on what I have, but my graph is not conclusive. So, but we can definitely see a max, but minimum, no. And if I make this go maybe more like so, then you can see that this thing is approaching 0, and same thing on this side. Okay. And then we have what we call a local extrema or relative extrema. Now, for local extrema, we're going to look at an open interval inside the general domain. So remember, the global looks at the entire domain of the function, whereas the local looks at extrema or maximum, minimum in a local zone over an open interval from A to B. So again, the definitions are similar to the one above. The key difference is that now C is inside of an open interval. Okay, that's the difference. It's not over the entire domain. And we're going to call these L max, L min for local max, local minimum. Okay, remember, so this is local to an open interval inside the bigger, possibly, domain of the function. Okay, now here I have a couple of notes for you. One is that the local minimum could be larger than a local max elsewhere, and vice versa. A local maximum could be smaller than a local minimum elsewhere. Okay, so for example, let's say I have something like this, and if I look at if I look at just the interval here, let me make this differently. There. And if I look at this local minimum over here, this would be a local min, right? Because there's no point lower than that. And that local minimum is going to be greater than a local max elsewhere. Well, my local max is here. This is an L max. And that's what we mean by that expression. The local minimum is higher than local max in another interval. Okay. And the local max could be lower than the local minimum elsewhere. So you can make it that way also. Okay. Now, the point corresponding to a local extrema, the tangent line is either horizontal or the graph has a corner or a cusp. That means the tangent line is actually vertical. So the case where I have a corner point, there is a tangent line. And the case where there is a cusp in the graph, the tangent line here is actually vertical now, right? And that means the function is not differentiable at that point. And that's what these two mean. So remember, if the tangent line is horizontal, then on the graph we have a corner point. And if if the tangent line is horizontal, then we have to have a local extrema. And the tangent line could be horizontal, by the way, not necessarily at the corner point. So for example, if I have a parabola like this, for this graph, there is no corner point, but the tangent line is horizontal. And therefore there is, it looks like in this case, there's a local max. Okay. So, there we have it. Now we're going to take a look at a very powerful theorem here. It's called Fermat's theorem. With the Fermat theorem, it goes something like this. If a function has a relative or local extrema at a number c inside of an open interval, then either the derivative must be 0 or the derivative does not exist. That is, again, the function is not differentiable at that point. So those are the necessary conditions for having relative extrema. So keep that in mind. Either the derivative at that point must be 0 or the derivative does not exist. Now, the proof of this, I'm outlining a proof of this one for a case where there is a local minimum. In the book, they have the proof for a case where there is a local maximum. So between the book and this one, we covered both extremas. So I'm going to suppose that f at c is a local minimum. That's a given. Okay, if it's a minimum at c. Well, if f prime at c doesn't exist, then that's what Fermat's theorem says, right? It says if it has an extrema, then f prime at c doesn't exist. So there's nothing to prove here, okay? And again, that's if f prime at c doesn't exist. But look at the other case. Let's say for the case where there's actually a local minimum and it has to be where f prime at c must be 0. So this time, by definition of a local minimum, remember this is the definition of local minimum, I mean there is no point lower than f at c. So if I look at h here, h is a number that is not 0 and it's in the neighborhood of c. So f at c plus h minus f at c has to be greater than or equal to 0. That's because of our supposition, because we have a local minimum. Okay, so if we have a local minimum, then this must be true. So that says f at c plus h minus f at c greater or equal to 0. So that means the difference here between these two functions must be positive to be greater than, or it could be 0. The lowest it can be is 0. Okay. Now, by our hypothesis of the theorem, because we assume that there is a local minimum, so we can say that the limit of the difference quotient exists, right? So f prime at c, which is defined as the limit as h goes to 0 of f at c plus h minus f at c over h, this limit will exist. Now, next we're going to take a look at h from two directions, coming from the right and another coming from the left. Now coming from the right, that's h0 from the right. Okay, so f at c plus h minus f at c over h, this has got to be positive or 0, worst case. Okay, it is positive because h is positive. We're coming to h from the right, so h must be greater than 0. So h is positive and the numerator is positive, right? That's because it's a local minimum. That means this expression, the first expression, is greater than this expression. Okay, so if the numerator is positive, denominator is positive, then this must be positive or 0. The worst case, the lowest value can be 0. On the other hand, f prime at c, if I approach h from the left now from the left, we know h is negative, right? And the numerator, we just said earlier, the numerator is positive. So we have a ratio of positive to negative, right? Which will be negative in this case. So we actually have arrived at a statement such as this one. From the first part, we establish f prime is positive, and then h going to 0 from the left, we establish that it's got to be negative. Now, at that point, simultaneously, it cannot be greater than and it cannot be less than. So the only viable option is equal to 0 between the two expressions, between the two limits. So that proves that f prime at c has to be 0. Okay. And again, the proof we're assuming there is a local maximum, and the proof is in your book. Now, it's important to note that the converse of Fermat's theorem is not true. And what does the converse say? The converse goes like this. Let's say f prime c equals 0, then f doesn't necessarily have a max or minimum. Remember, if it has a max or minimum, f prime at c must be 0 or doesn't exist, right? So if f prime at c is 0, then it doesn't necessarily need to have the function need to have a max or a minimum. And I have two instances here. I've made up two examples of functions here that actually at c the slope of a tangent is 0. So f prime at c is 0 in both of these graphs. But if you note, neither of those 2 points at c are max or minimum. There are other points higher than those and lower than those 2 points. One being this, the other one being this one. Okay, so that just goes to again illustrate that the converse of Fermat's theorem is not true. Okay, now a corollary to this reads that if f prime at c exists and if f prime at c is not 0, so the derivative at c exists but it's not 0, then f at c cannot be the max or the minimum of the function. So f at c is not a relative extremum of the function f. So in other words, the conclusion, we can put it all together like this. For every point where f has an extrema, okay, then any one of these three could be true. One is that an endpoint of a closed interval, that point must be an endpoint of a closed interval, which in this case we have what we call an endpoint extrema. Or if we have an open interval, the point where f prime doesn't exist, and on the graph this translates usually into a corner point or a cusp on the graph of the function. And in part C, a point that is interior of the interval where f prime of x is 0. That is, the tangent line is 0. So remember, the extrema must be either inside an interval where the derivative is 0, right? Yeah, I was going to change x to c here, f at c, because we're talking at the point inside. Okay. F prime at c is 0. And again, or the derivative does not exist. Let's look at the other idea in this section, is that of a critical number of a function. So this time a number c inside the domain of the function. We call it a critical number of f if either the derivative is 0 or the derivative at that point does not exist. Okay, so in this case, c is called the critical number. Okay, a number c is the critical number. If one or the other condition, not both conditions must be met, one or the other. Okay. Now, if f prime at c is 0, then c is inside an open interval inside the domain. Okay. And if either f at a or b, the endpoints that is of a closed interval, f at a or b is an extrema, then the endpoint extrema is what we call them. Okay. Now this last bullet, this one has nothing to do with the derivatives. Okay, we're just giving you a definition, a terminology. If the max or minimum occur at the endpoint of a closed interval, then they're called endpoint extrema. Okay. And again, to tie this down for Fermat's theorem again, so to make a conclusion about Fermat's theorem, it states that the relative extremum of f of x can only occur at the critical number of a function. And that pretty much calls Fermat's theorem for what it is. Okay, so in the exercises we'll see in a few minutes. If the question says or reads find the relative extrema, we're going to find the critical numbers of the function, and then at those points we got to look at the tangent line, and then we decide whether at that point the derivative is 0 or does not exist. Okay, at C. And we're going to finish this section using this last theorem, which is called extreme value theorem. Because there are no guarantees that the extreme of the function may exist, may not exist. So this extreme value theorem is a theorem that actually guarantees the existence of the max or the minimum. If a function is continuous, however, though, that's very important. The function must be continuous on a closed interval. Okay, so if a function, this is how the theorem goes now, which we state without proving it. If a function f is continuous, means there is no breaks, no holes, no jumps, no asymptotes. Okay, if a function is continuous on a closed interval, then f must have a minimum and a maximum at least once inside of that closed interval. So that's great. We love closed intervals and we love continuous functions because for those we know there is a maximum and there is a minimum and we can find them. So here I have three different graphs here. The first one, and all three of these are continuous functions, by the way. So first one, notice there's a max, there's a min, and I have closed interval for all of these. The middle one, closed interval from A to B. There is a minimum and there's a maximum. And the last one is a case where there's more than one min or max. The case for the extreme value theorem. Okay, and so there you have it. Now we can take a look at some exercises. So I'm just going to bring up these exercises and we're just going to work these together. Okay, so in this segment of the exercises 1 through 6, question reads, you are given the graph of a function f defined on the indicated domain. Find the absolute maximum and absolute minimum value of f if they exist and where they are attained. Now, assuming the domain is what we're looking at here, that's why it's called now the word absolute, because we're looking at over the entire domain now that is defined. Okay, so absolute max means the point where there's absolutely no point higher than that on the graph. So in this case, it looks like the absolute max is going to occur at 1. So part A, that's where absolute max is, right? The value of the absolute max, by the way, is 3. Where it occurs at, where it is attained at, is at 1. So to answer the question correctly, the maximum, absolute max, is 3, and it is attained at 1. Now notice here, this would be some kind of a minimum, right? But it's not an absolute minimum because there are other points. See, that's at 2. These points are all lower than that, so that cannot be a minimum, right? It would be a minimum if we had some interval that, let's say, is closed interval from here to there. But it's not the absolute. And because the function keeps going down forever, it's not bounded, so this one does not have a minimum. Looking at number 2. In number 2, the minimum at 0, and the value of the minimum is also 0. Notice there is no point lower than that. However, there is no max since it just shoots up indefinitely. So minimum 0, attained at 0, and again unbounded, there is no max. And I'll let you do number 3. Let's take a look at number 4, for instance, this one. In number 4, notice that there is no maximum because it's an open circle, right? So the value of 2 is not inclusive, right? The value of function at 2 is not included. So the function is not bounded above. Therefore, there is no maximum. Now, looking at the minimum value of the function, remember it's a constant function, and any point here could be a minimum. So the minimum is -2 in this case, in exercise number 4. And the minimum is attained at for x greater than 0. All right, because x cannot be 0 because we have open circle at 0 here. In other words, f at 0 is 0 right in here, right? That's f at 0 equals 0. So for x greater than 0, the minimum in this case is going to be -2, right? For any one of these, at that point, this point, this point, this point. So it's attained at any one of those points. All right, and if you look at number 5, if you're curious for number 5, looks like again the absolute max is here and the absolute minimum is here. So max 37, minimum -5, right? Attained at 1 and 5. Let's take a look at the others. Okay, so let's begin with exercise number 8. In exercise number 8, the question reads, sketch the graph of the function and find its absolute max and absolute minimum values, if any. Now these functions, by the way, are such that we should be able to graph these without the use of a graphing calculator. We really need to know how to graph these ourselves without using technology, because these are basic functions that we are familiar with, so we don't really need a graphing calculator. So let me begin with number 8. G of x is -3x plus 2, so we have a line on a closed interval from -1 to 2. Okay, so we can actually graph the lines just like we do all lines, right? Here's the vertical axis, here's the horizontal axis, this is x and y. Now for this one, again, the y-intercept is at 2, correct? Y-intercept at 2, slope's -3. So it's going to be a rather steep line. We don't need to have exact like plotting points. This is good enough for what I'm doing here. That's why we graph these by hand. As long as we have realistic graph, that's good enough. So there's a y-intercept. Now we're given, so I'm not going to put arrows at the endpoints of this line, okay, because we are given actually a closed interval from -1 to 2, right? So since we have a closed interval, I'm going to go, here's -1, and call this 2. Now it's open interval at 2, right? Open interval at 2, so it's going to be, the point's going to be, we're going to use open circle there, it means not included. Okay, and there, to emphasize that. Now at 2, g at 2 is -3 times 2 plus 2, or -4. So that's what this is. This point is at -4. And then when x is -1, g at -1 is going to be -3 times -1 plus 2, or 5. So this point's going to be included, and it's going to be, there you go, that's going to be at 5. So this is -1, 5. Okay, and of course the graph isn't drawn to scale. All right, but good enough, we can get that information from the graph. Again, the question is asking for maximum or minimum, right? And these are absolute. They call them absolute because we are a prescribed domain. Suppose that's all that function is good for in that domain. So what do you think? Maximum? There's going to be a maximum. The maximum is 5, and it is attained at x equals -1. And what about minimum? Now notice, because of that open circle minimum, we can't say minimum is -4 because we have open circle, means it gets very close but not quite -4. So we're just going to say none. There is no minimum in this function. I mean, it's darn close to being -4, but this is mathematics, so for our purposes it doesn't exist. In number 12, h of x is x squared plus 1, and the interval is open interval, half open, -2 to 1, close that one, right? Now for this one, this is a basic parabola, right? The graph of a parabola is going to, let me make it like this. The graph of this parabola is going to look like so. At -1, actually at -2 here, there you go, -2 to 1. So at -2, it's going to be -2 squared. 4 plus 1 is 5, except it's going to be an open circle, right? So I'm going to make it, let me do this, let me adjust my tick mark. I'm going to call this height a height of 5, and this is where -2 is now. There. Now the other portion of this, when x is 1, 1 squared, 1 plus 1 is 2. So I'm just going to go up here and close it. Now because again at -2 there's parentheses, remember that's an open circle. I just want to make sure we see that. Okay, and we are good with this one. Okay, and this was 2. So this time maximum, none. There is no max because again this point is not included at 5. And notice this is 2 is a local max, but it's not absolute max. That's what they ask. Absolute max means over the domain. And as far as the minimum goes, yes, there is a minimum. The minimum occurs at 0. So minimum is 0 at x equals 0. So keep in mind again, the max and minimum we're talking about here are the values of the function, not the x values. In number 18, for instance, now 18, we have absolute value of 2x minus 1. So this is g of x equals absolute value of 2x minus 1 on interval from 0 to 2. Okay, and for the absolute value function now, I can do this one here. Let's see, when x is 1/2, y is 0, right? 2/2 times 1 is 1 minus 1, 0, and then you have this general absolute value graph. So that's what number 18 is going to look like. Now, of course, this is only from 0 to 2, right? So this portion goes only this much. It only goes to 0. And at the right side, at 2, we're just going to stop it at 2. So let's say right in here, we're just going to bound it by 2, at 2. And it's bounded by the value 2 times 2, 4 minus 1, 3. There you go. This point, 2 comma 3. And of course, the open circle happens at when x is 0, y is 1. Okay, there's the graph of the absolute value. Now, let's go with minimum. Minimum is this point, right? No point lower than that. So the minimum of the function is 0. And again, we attain that as x equal to 1/2, right? At x equals 1/2. And in the case of absolute maximum, well, let's see, the absolute maximum is going to be what? That was, minimum. Absolute max is this one right here, right? That's going to be 3, and that one is attained at x equals 2. This point doesn't matter. It's not part of the graph, and it's not a max. So there's point higher than that at 2. Okay, so there we go. We've got number 18. Now let's take a look at number 24. In exercise number 24, we have f of x is equal to square root. It's a piecewise function, root 4 minus x squared and negative square root of 4 minus x squared, right? If x is between negative 2 and 0, so that's negative 2 comma 0 parentheses at 0, and then 0 to 2 inclusive. Okay, so let's take a look at number 24 here. Now, in order to graph this one, number 24, let me actually write this. If we have y is equal to plus or minus square root of 4 minus x squared, we can square both sides and we get y squared is 4 minus x squared. Add x squared to both sides. So we recognize this equation, right? X squared plus y squared is equal to 4. Now x squared plus y squared equals to 4. That's going to be the equation of a circle, right? And that's what I have my circle here. Now the upper portion of the circle, that's this portion of the circle, is going to be square root of 4 minus x squared, which is the half circle, a semicircle, right? The radius of this circle, by the way, is 2, right? Negative 2 to 2. And the lower segment of that circle, right, the lower part of the circle is going to be this one, right? That's the lower part of the circle. And that lower portion is given by the negative square root. So this is negative root 4 minus x squared. So it is possible to actually put those two together and make up the full circle, and that's what the piecewise function does here. Now, the exception is that from negative 2 to 0, we have the upper circle. So that upper circle goes from negative 2 to 0, right? In other words, only this portion of the circle is what we need from negative 2 to 0. At negative 2, we have a closed circle, and at 0, open circle, because that's not included, right? Because 0 is not included. So that means for that upper circle, we don't need this portion, what's in Q1. Now, for the lower segment, that's only good from 0 to 2, right? That means just over this segment right in here, from 0 to 2. So we don't need this segment of it, right? So I'm going to remove this portion of the lower circle. And now we have, that would be the graph, the part of the circle that we need is right there. Okay, now 0 is included in the interval, so that's going to be a solid circle at 0, but then 2 is also solid. See, I'm looking at the endpoints here. 0 and 2 are included. So actually the endpoints of that lower semicircle, an arc of a circle, is included. And this is the graph of this function. Okay, and so there we have it. So it looks like, and because the radius of this is 2, so that's 2, this is negative 2. All right, let's do our max and minimum. So it looks as if, again, there is no maximum. Maximum is darn close to 2, but there is no maximum because it doesn't quite reach 2. So I'm just going to say for maximum, none. What about the minimum? The minimum, the lowest point on the graph of the function is here. The minimum is negative 2, and that one again is attained at x equals 0. So that's what that is. Okay. And we have this exercise done, number 24. Let me bring some more up here, and we'll look at some more. All right, let's take a look at this exercise now. So we're going to do number 28. In exercises 25 to 42, the question reads, find the critical numbers, if any, of the functions. That's all we want to do, find critical numbers. So let's begin with number 28. In exercise 28, the function h of t is equal to 6t squared minus t minus 2. Now remember, the critical numbers by definition are numbers where the derivative is 0 or undefined or does not exist. So for all of these, we first need to find the derivative. This is going to be 12t minus 1. Now this derivative function is a linear function, and its domain is already in numbers, means the derivative always does exist. So we're going to set it now equal to 0. That's why, because of definition of critical number, and solve for t. So that means 12t is 1, or t is 1/12. So t 1/12 is going to be the critical number of this function. That's all we're doing here, just finding the critical numbers. Let's look at number 32. 32, f of x is 1/3 x cubed plus 1/2 of x squared plus 2x minus 3. So again, to find the critical number, we're going to take the derivative. That's 1/3 times 3x squared plus 1/2 times 2x plus 2. That makes it x squared plus x plus 2. Okay, and now we need to set this equal to 0, right? And solve, set it equal to 0. Now this function is a quadratic function. So usually with quadratic functions, we try to factor them when we set them equal to 0, and if they're not factorable, we use the quadratic formula. Now for this one, let's see, remember how we factored them? We set them as binomials. You go x, and then looking for two numbers that multiply to 2, and let's say add to 1. Well, 2 is prime, so those are my only choices, or -2. -1 would be another. The OI combination in FOIL, in this example, I cannot find numbers that work to where the OI adds up to 1. So this isn't factorable. The question, does it have a solution, a real solution? We're looking for, remember our set S is set of real numbers. Okay, in other words, the x-axis, we're looking at x-axis real numbers. Now for this one, if I look at the discriminant of this one, remember b squared minus 4ac, that's going to be 1 squared minus 4 times 1 times 2. The discriminant is -7, less than 0. So this one has complex roots, right? Complex roots. So that means because discriminant is negative, therefore there are no real solutions, so no critical numbers here. So in number 32, no real solutions. That means no CN stands for critical numbers. Number 32 does not have a critical number. Okay, number 32. All right. And let's take a look at number 36. Okay. In number 36, here we have again a function. The function is h of z is equal to z cubed -8, -5, sorry, I look at the one above it, -5, z fifth. I was looking at the one above. Okay, that's z to the 5th negative 5z cubed plus 10z plus 4. So let's do h prime z. That would be 5z fourth negative 15z squared plus 10. And then we need to factor this one, right? Now, for number 36, we can actually factor a 5 out to make it a little easier, right? So it's going to be 5 by z fourth negative z 3z squared plus 2. And then again, these are the type of quadratics where in intermediate algebra classes they're called quadratic in form. That means we may be able to see them as binomials, as quadratic expressions, which is product of binomials. So I'm going to go z squared, that product is z fourth, and then two numbers multiply to 2, middle value negative 3, let's go negative 1, negative 2. Okay, so that would be the factored form of this one. And then at the same time, we're going to set it equal to 0. Why? That's definition of critical number, again, where the function is 0 or undefined. Now again, this is a polynomial function. So polynomial functions are always defined, and this derivative, the derivative is a polynomial function. So there's no point where f(h) prime does not exist. Usually that happens, h prime doesn't exist when there is a denominator. And we have a variable in the denominator. We'll see that in a moment. Okay, let's solve this. Z squared minus 1 is 0, or z squared minus 2 is 0. Therefore, z squared could be 1. Therefore, z squared could be 2. So we get plus or minus 1. And z is plus or minus square root of 2, taking the square root of both sides in each. So we have actually four critical numbers in this case, right? The four critical numbers are negative root 2, negative 1, 1, root 2. These are the critical numbers. So later on, we're going to say, well, if there is an extrema of the function, it has to occur at one of these, or it's an endpoint. So that's number 36. Let's take a look at number 38. Number 38, we have 4t to a third plus 3t to 4/3. And this is number 38 again. The expression g of t was 4t to 1/3 plus 3t to 4/3. Okay. Now let's do the derivative. G prime using the power rule, that's going to be 4/3. That's 1/3 times 4. Third minus 1 is negative 2/3 plus 4/3 times 3, right? That's going to be 3 times 4/3. The 3's cross out. 4/3 minus 1 is 1/3. T to 1/3. Okay. Now, in this one, we need to, so this is the derivative. Oh, it's very important, by the way, that we simplify these derivatives, okay? Because next step is crucial in our next step. So I'm just going to factor 4, okay, because both terms have 4 in them. And then let's factor, let's see, this is what I'm going to do first. I'm going to write this as 4/3 t to 2/3, right? Negative exponent rule, plus 4t to a third, right? Now we need to combine these fractions. We do need to simplify the derivatives from now on because of what we're about to do. The LCD here is 3t to 2/3, right? So I'm going to multiply the second expression by 3t to 2/3, top and the bottom, so I can get LCD. Okay, and remember, I'm going to factor a 4. Both of these have 4 in them, so I'm going to factor a 4. That makes it 1 from the first expression, plus 3t to 2/3 from the second expression. Okay, And there you go. That's how we combine these. Okay. So I have, oh, actually, I didn't do that part right. In here, in the numerator, t to a third times t to 2/3, that's t to 3/3, or it's just t. Actually, that works out nicely. There. Now I'm going to copy that over here. So it's 4 times 1 plus 3t over 3t to 2/3. Okay. Now, that's our g prime. Okay. Now notice, again, by definition, critical numbers are numbers where the derivative is 0 or it is undefined. G prime t, let me just write that. G prime t is undefined where the denominator is 0, right? Division by 0 is undefined, right? So so we need to solve this. This is easy. Raise both sides to 3/2 power, so t would be 0, right? So that's the only value that makes this 0. Or g prime t, set it equal to 0. That's another way a critical number can be found, where the derivative is 0 or undefined. Now, in the fraction, if g prime is to be 0, then the only way this fraction can be 0 is if the numerator is 0. So that means I need to set 4 times 1 plus 3t equals 0. You can divide both sides by 4. So this 4 really doesn't play any role in finding the 0. That's 0. So in other words, we get 1 plus 3t equals 0, from which t is negative 1/3, right? Subtract 1 divided by 3. So there are two critical numbers for this one. 0, which makes the derivative undefined, means function is not differentiable at that point, or t equals negative 1/3. Now it's important when we find these, by the way, that these fall in the domain of the function. Okay. Now the domain of this function, because it's cube root, right? It's cube root here, cube root of t, and cube root here. The domain of cube roots are all real numbers, so both of these numbers are within the domain. But we have to check. And up here, the same thing. All of these numbers are in the domain of the function here, right? Because the function was polynomial function. So there's going to be instances, sometimes we'll see maybe later, where you find the critical numbers, but they fall outside the domain of the function, and therefore we just discard them. We just don't use them if that's the case. So there you go. I guess we're good in this segment. So let me grab more exercises. They're down here. I'm just going to move them up, and we will work more of these exercises next. Okay, let's take a look at these exercises. In exercises 43 through 60 means all the ones that I'm going to be looking at. I'm going to look at 4 of these in this segment. Find the absolute maximum and absolute minimum, if any, of the function. So this time we actually want to find the absolute max and absolute minimum. Now notice one thing, by the way, all of these intervals that we are given, all of these intervals, they're all closed intervals, right? You see that? Okay, so that means anytime we have closed interval for extrema, we need to check the endpoints, okay? Because we could have endpoint extrema. And the other thing we need to check, we need to find the critical numbers, and we need to check the value of the function at those critical numbers, compare those against the endpoints, and then decide which is the true max or minimum, okay, over the domain. So let's begin with exercise number 46. In number 46 here we have f of t is equal to a function of t is given by 2t cubed, negative 2t cubed plus 3t squared plus 12t plus 3 on negative 2 to 3. Okay, so let's actually do this, just so this is a good practice to do. Anytime you're given a closed interval, right away do your endpoints. Do f at negative 2 and do f at 3. Okay, so you don't forget it in the end. I usually do that. Now f at negative 2, you plug in negative 2 for t. This is just not calculus, this is just simple algebra now. Negative 2 squared plus 12 times negative 2 plus 3. And if I did this right, I got 7. All of these add up to 7. Okay, now f at 3, do the same thing kind of. You put 3 cubed plus 3 times 3 squared plus 12 times 3 plus 3. If I did this one right, f at 3 should become 12. So that's there. Now these could be a max, this could be a minimum, right? Okay, and by extreme value theorem, we are guaranteed, because the function is continuous, so we are guaranteed that there is a max and there is a minimum. So the only thing that's missing right now are the critical numbers. So let's do that. Cn, critical numbers. For critical numbers, we take the derivative. Again, this is a polynomial function, so its domain is all real numbers. So any critical number we find, it's going to be in the domain, but we always check to make sure that we are in the domain indeed. So let's do f prime. F prime is going to be negative 2 times 3t squared plus 3 times 2t plus 12. That's going to make us negative 6t squared plus 6t plus 12, right? And we can factor a negative 6 from this, and that's going to make it t squared minus t minus 2, right? So we have our polynomial. And this one, again, a quadratic expression. We are hoping that it is factorable, so let me try that. I go tt, now two numbers multiply to negative 2 here, and I'm going to go negative 2 and 1, and the oi plus 1, negative 2, yeah, that should do it, minus 2. The oi combination gives me negative t, so this is the right combination. Now we're going to set it equal to 0. Now at this point, by the way, at this point you look at the derivative function and you set it equal to 0, and also if there is a denominator somehow, you set that also equal to 0, because the derivative function in this case is polynomial also. So it's defined everywhere. So there is no place where f prime is not differentiable. It's differentiable everywhere. But if there are points where the derivative function is not differentiable, we need to find those also. Okay, so let's set this equal to 0, t minus 2. Each factor could be 0 by zero factor theorem. So we'll pick up two numbers for which t is 0. Those are our critical numbers. Our critical numbers are 2 and negative 1. Now if you note, let's see, up here we have negative 2 and 3. Good, so let's try this. Now we're going to do f at 2, and then we're going to do f at negative 1. So f at 2, that's when you put 2 into the function. Okay, so f at 2, I actually have tried this one. I plugged it in my scratch work. Okay, and f at 2 ended up being 23. Okay, and f at negative 1 ended up being negative 1. So please check these to make sure I did it right. But all you got to do is plug into this function. Okay, simple arithmetic. Now let's compare them. Remember, we have these numbers now. Let me bring them from up here. F of negative 2 was 7, and f at 3 was 12, right? So at this point, we're going to look for maximum and minimum. The max is 23, right? Attained at 2. So we're just going to write that. Max is 23, attained at x equals 2. And minimum of this function is going to be 7, and it is attained at x equals -2. And there we have them. Okay. And that's all. We are done with this exercise number 46. And you're welcome if you really want to. This is purely optional. You're welcome to just graph these and kind of see on the graph what's going on with the function. We're not interested right now. We will be graphing functions extensively in a few sections, but not in this section. This time, let's look at this more elaborate function. We have square root of u number 50, square root of u over u squared plus 1 from 0 to 2. So remember, first I'm going to, before I forget, I'm going to do g at 0. That's going to be 0 over 0 squared plus 1 or 0. And g at 2 is going to be square root of 2 divided by 2 squared is 4 plus 1 or root 2 over 5, whatever that is. Okay, next we're going to proceed with our derivative. Now, right, in number 50, let's take the derivative. So to do the derivative, I'm going to use the quotient rule. Okay, and g prime of u will be square the denominator, so that's going to be u squared plus 1 squared. Repeat the denominator times derivative of the numerator is 1 over 2 root u. Okay, minus the numerator, minus 2 minus u root u times derivative of the original denominator, which is 2u. Right, not this denominator, the one we squared, the original one. Okay. Now, for this one, just to get rid of complex fraction, I'm going to multiply top bottom by square root of u. Okay. And in fact, let's multiply top bottom by 2 square root of u because I see a 2 in this denominator. So I'm going to do 2 root u. And this is 2 root u on the bottom. And then distribute. 2 root u times this fraction. First fraction makes 1, so I just get u squared plus 1. And then we're going to distribute 2 root u times this expression. So it's going to be negative 2. Square root of u is just u times another 2u, the factor that comes after square root, this one. Okay, and then over the denominator. The denominator is 2 root u times u squared plus 1 squared, right? Okay, now in the numerator we can combine like terms, and g prime of u, all said and done, is going to be, so it's 2 root u, u squared plus 1 squared, and in the numerator, I'm going to get u squared negative 4u plus 1, right? Make sure I did this one right, so I get u squared plus 1. Oh, negative 4u squared. Yeah, that's right, because it's u times u. You get u squared. Negative 4u squared plus 1. So we have a couple of like terms in the numerator. I get 1 minus 3u squared over the denominator. 2 root u and u squared plus 1 squared. Okay, now let's focus on this derivative. Critical numbers are numbers where the derivative is 0. So I'm going to do two things. Well, first, let me go back to the original function. Okay, we're given 0 to 2. Okay, never mind. I was going to make sure my critical numbers aren't going to be in the domain, but we're given a closed interval anyhow, 0 to 2. Okay, next to find, so this is the Cn now, critical numbers. We're going to set it equal to 0. And also g prime of u does not exist. Remember the definition of critical numbers? places where the derivative is 0 or doesn't exist. G prime does not exist when the denominator is 0, right? Division by 0 for G prime. Now, in the numerator, if I said 1 minus 3u squared equal to 0, I get u squared is 1/3, so u is going to be plus minus root 3 over 3. It's 1 over root 3, but you can rationalize it. Okay. All right. Now, so we found two critical numbers so far. Now, the next we're going to look at the latter expression here. So we're going to find the zeros of this expression. So square root of u could be 0, or u squared plus 1 squared may be 0. Right? May be 0. It won't be 0 in this case. But okay, square root of u equals 0. Square both sides, so you get u 0. There's our critical number. Okay. Now, u squared plus 1 may be 0, or u squared is -1, and u is going to be plus minus root -1, which is plus minus I. These are not real roots, right? These are complex roots. Therefore, because we are looking for real zeros, so there's no way u squared plus 1 can be 0 with real numbers. So we're just going to discard that one. So our critical numbers, therefore, are that we can actually write. The critical numbers will be negative root 3 over 3. Okay. Or it could be 0 or root 3 over 3. There. Those are the critical numbers. And now, let's try these. So I'm going to go g at 0. G at 0, we go back to the original. But we've done g at 0, right? That was one of the endpoints. G at 0 is 0. So it just happened the critical number is one of the endpoints, right? G at 0. Let's try g at root 3 over 3. So g at root 3 over 3, that's going to be square root of u over u squared. So it's going to be square root of 3 over 3 over u squared, that's root 3 over 3 squared plus 1. Okay. And for this one, let's work this one. So that's going to give me square root of 3 root 3, right, divided by 4. That's what I'll get. Now let me show you how to get this one. So here's how, let me show you the work that led to what I have in here now. Okay. So in the numerator, the step before that, in this step before that, you can write this expression as root of square root of 3 over square root of 3, right? Break the radical into two parts. And then divided by, in the denominator, when you square the fraction, we're going to get 3/9 plus 1. And in the numerator, I have root 3. Now multiply top bottom by square root of 3. The root 3 here crosses out. In the bottom, I have root 3. And then 3/9 is 1/3, right? 1/3 plus 1 is 4/3. Okay. And 4/3, you can invert and multiply 4/3, becomes 3 times root 3 over 4 rad 3. Okay. And then 3 double root 3 divided by 4 root 3. Multiply top bottom by square root of 3. Okay, and this one gives me 3. Now, the square root, if it's 3, it's going to be this 3 times the other factor, the other radicand, which is root 3. I multiply the radicands, multiply 3 times that, right? Using the product rule of radicals. In the denominator, you have root 3, that's 3 times 4. The 3's cross out. And the result is what you see here. Okay, that's how I got that number. Okay. Pretty wicked. Now, that's going to be g at root 3 over 3. And g at negative root 3 over 3 is going to be the same thing, only negative. Let me see. No, let me see. G at negative root 3 over 3. You can also, how about this? Instead of root 3 over 3, let's go 1 over root 3. How's that? But the one thing is, at negative 1 over root 3, remember, 0 to 2. This is our focus, is from 0 to 2. So we're just not going to even bother with that. Yeah, this is, I'm just going to say this is not in domain. So we won't even bother with that. Okay. And even, again, the g root 3 over 3, let me try this one this way. If I have 1 over root 3, without rationalizing the denominator, would have been easier. That's 1 over root 3 squared plus 1. And I have square root of, that's what, it was a square root of u. Okay, so square root of 1 over root 3. That may have been easier to work this way. The denominator is 1/3 plus 1, 4/3. Right? That's 1/3 plus 1 is 4/3. The numerator, square root of 1 over root 3, that's square root of 1 over square root of a square root of 3. Square root of 1 is 1, right? So that's just going to be 1 over root 3. 1 over root 3. Okay. And you can work that one. Anyway, so it may be easier to do it this way. I just thought I put that out there. You can try it. Since I've already done it, I'm just going to stay with this one. All right. Now, let's take a look at our work here. So we have g at 0 is 0. G at root 3 over 3 is root 3 over 4. Now, this number, root 3 over 4, turns out to be approximately, when I did it on my calculator, I get about 0.6. Okay, that's what that number turns out to be, 0.6. In the very beginning, g at 2 is root 2 over 5. G at 2 was root 2 over 5. Now, root 2 over 5 turns out to be about 0.3-ish. That's about 0.3. Okay, so now we're done. Maximum is going to be, instead of 0.6, we're going to say root 3 divided by 4, and it's attained at x equals root 3 over 3. And the minimum is going to be 0, and that's attained at x equals 0. Okay, and there you have it, the answer to number 50. Again, if you noted, the algebra is what kind of gets in the way of these. This was kind of a long, detailed, drawn-out exercise. Let's take a look at number 58, the last in this segment. This time g of x is cos x negative sine x on 0 to 2 pi. Cosine x minus sine x. Okay, so number 58, g of x is cosine negative sine x over the interval from 0 to 2 pi, inclusive. Okay, so this is going to be, again, straightforward. G prime x is going to be derivative of cosine, negative sine, minus derivative of sine is cosine, right? Negative sine x minus cosine x. Now we know that this is, again, the derivative is continuous everywhere, right? So there's no place where g prime, where the function g is not differentiable. It's differentiable everywhere. Okay, so we're going to set it equal to 0 and solve it. Well, sine x equal negative cosine x, right? You can multiply both sides by negative. That becomes sine x plus cosine x, right? When I set it equal to 0, I could. I'm not saying in the beginning to do that. And then there you go. You get your next step is that. Okay, now sine x equals negative cosine x. Let's see, how do we solve this one? We can divide both sides by, let's say, cosine x. So by cos x by cos x, and we get tangent of x is equal to negative 1. Okay, now let's see. Tangent is negative 1, so we need to know for what, that's going to be special angle, right? Tangent is negative 1 at 3 pi over 4, right? And 7 pi over 4. Those are the places where tangent is negative 1, right? On that interval 0 to 2 pi. So now remember, I forgot, we always have to try the endpoints before I forget, because we could have endpoint extrema. So g at 0 is cosine 0, negative sine 0. Cosine 0 is 1, sine 0 is 0. The answer is 1. At 2 pi, you get exactly the same thing, right? At 2 pi, you get cosine 2 pi. So because you're complete circle back to where you started. So it's 1 minus 0 or 1. Okay, so here, if this ends up to be a max or minimum, then we achieved it at more than 1 point. Now, we need to try, oh, I didn't finish. So the critical numbers here are 3 pi over 4 and 7 pi over 4. And then g at 3 pi over 4 is when we put 3 pi over 4 for cosine and then sine. So we have cosine of 3 pi over 4 negative sine of 3 pi over 4. Now cosine of 3 pi over 4, the reference angle is 45-degree angle, right? That's 1 root 2. So cosine is going to be what? Negative, because we are in the second quadrant. Negative 1 over root 2. Sine is going to be positive 1 over root 2. You get two like terms, so it's negative 2 over root 2, or just negative root 2, right? That's what it turns out to be. And g at 7 pi over 4 ends up being cosine of 7 pi over 4 negative sine 7 pi over 4. Cosine of 7 pi over 4, again, the reference angle is 45 degrees. Because the angle itself is in the fourth quadrant, cosine will be positive, sine will be negative. So that's 1 over root 2. The reference angle is 45 degrees. Negative sine, because we're in the fourth quadrant, sine would be negative 1 over root 2. And in this case, negative. So that's going to give me 2 over root 2, or just root 2. Right? Okay, so we got 4 values here. G at 0, 2 pi, 3 pi over 4, and 7 pi over 4. So we can finish this one. The minimum is going to be what? Minimum is going to be negative root 2. Oh, let's see. Yeah. Minimum is negative root 2, and that's when x is 3 pi over 4. At x equal 3 pi over 4. And our maximum is going to be square root of 2, which is 1.4. Is root 2, and that's attained at when x is 7 pi over 4. Okay, and that's what number 58 looks like. So the minimum is negative root 2, maximum positive root 2. And there you have it. We are done with exercise number 58.